Okay, good morning. I think we can start the session. If you can hear me, you can. Yes, thank you. Thank you. Okay, that means what we will do this week. This week, we will start chapter 10. And in chapter 10, we have two things. We have parametric equations, and we do have a polar coordinates. Okay, that's we have two different topics. And this week, we will cover section 10.1 and 10.2, and we will talk about parametric curves, parametric equations only. Okay, that means let's start. 10.1, and hopefully, because they are relatively short sections, not many complicated concepts, that means hopefully I can cover two sections today, and tomorrow we can have just a review session, okay, or just like office hours. Okay, let's start. Some windows are. I will. Okay, that's me. Let's see. Let's see what we have. Okay, that's me. Parametric equations. What it is? It's me. Parametric equations. Let's look at this. Parametric equations are basically like a set of quantities that will define explicitly a curve. Okay? That means having a curve in the xy plane. Let me draw something. Oh, hang on 1 second. Yeah, we will go here. That means having a curve, I don't have to draw it, I have here. Having a curve in the xy plane, not always the curve will be a function. And what do you think? Is this curve represent a function? Of course, no. Yes, thank you for answering, because we remember from algebra class in high school or maybe even middle school, the vertical line test. If the vertical line is intersecting the curve more than once, then of course this is not a function. The curve doesn't satisfy the definition of the function. That means this is not a function, but it's still a curve. Okay, and sometimes we can still use the equation y with respect to x. We can still do it. Or the nice example is the parabola other way. Yeah, like something like that. We know that this is not a function, but I can switch and I can have function x with respect to y, for example. Yeah, that means I can have the equation. But even looking at this curve, it's doesn't have a nice regular shape. It's a little bit complex, I would say. That means not always we will be able to get the equation y in terms of x or x in terms of y. Okay. Then what we will do, as mentioned, we will introduce another variable which we will call parameter, and we will create a parametric equations. Which this means that x will be defined explicitly as a new formula, f of t. The t will be the parameter. And y, the coordinate y, will be also defined as a new quantity, new function, explicit function, g at t. And as we can see, we will define x and y. And if we will think about possibly a particle moving along the curve, x and y will give me the position. That means the function f of t and g of t will give me the position of this particle with respect to x and y, of course, but x and y is defined in terms of the other quantity. Okay? That means just f of t and g of t means the parametric equations. I can remove my parabola because parabola is still not a problem. And then let's see. Suppose x and y are both given as a function of the third variable, t, and we can use any letter, any variable, but not always, but usually the t represents the time what was the time of the position at this point. That's the reason that we're using t. Okay, and we of course call parameter, and x is defined as a function f of t, and y is defined as the other function which also depends on t, and both of them we call parametric equations. Okay. And parametric curve, I need an equation for x, I need an equation for y, and if I will combine them together, plot the points, connect them, I will create a parametric curve. That means just simply the parametric equations for the x and y create a parametric curve. That we can plot in the coordinate plane. And we will practice. Okay? We will practice how to plot a curve which is defined by parametric equations. Okay, and a few notes, as always. That means, as I mentioned, that t will not always, but represents the time. That's the reason that we have t. And x and y will be the position of the particle if we think about a particle moving along the curve. Okay. And what is important, because since x and y is defined in terms of the third variable time, like we will indicate the direction of this motion, of the movement of the particle. Like, let's say time was 0, then what is the value of x, y, what's the position? And then after 1 second, let's say time is 1, then we will substitute instead of t1 and check the position x, y. That we will always have some points. Let's say this is t at 0, this is t at 1, this is t at 2, and then we can connect, but what is important? The important will be the direction. As t increase, then we have to indicate how the curve is like created. Okay? That means this is one thing that is a little bit different than just the x and y, because if I will have parabola or any other like curves, doesn't matter how I draw it, but for this one it will be important because we have to trace the time t. Okay, and let's look at the first example. Let me sketch and identify the curve defined by the parametric equations, and x is defined as a t squared minus 2t, and y is defined as a t plus 1. Okay, probably we don't see right away. We see some square, quadratic form, we see the linear form, but we don't know, we can't really guess what curve it will be. Okay, that's what we will do. And I have a table. T, since we do not have any restriction for the parameter t, I can pick any number. Okay, that means I can say that t could be any real number. Okay, and if t is any real number, we can see that x also will be substituting any number, we will get any number, positive, negative, and the same for y. Yeah, that means no restriction. Sometimes we do have restrictions, but we will see. Okay, that means I pick a few values, few negatives, 0, few positives, and then I will simply compute x and y, following the formula. And I will plot these points. That means it's relatively easy, like almost like an Algebra 1 class. Okay, look at my arithmetic and help me if I make some mistake. I will take -2 and substitute for x. X is defined, I can copy maybe on the top. X is defined as a t squared minus 2t. Y is defined as a t plus 1. Oh, t plus 1 is easier. Let's start with t plus 1. -2 plus 1, -1. -1 plus 1, 0. And then 0 plus 1, 1 plus 1, 2 plus 1, 3 plus 1, 4 plus 1. That's easy. Let's do this. -2 squared is 4 minus -2 times -2, actually 8. 1 plus 2, 3. 0 will give me 0. 1 minus 2, -1. 4 minus 4, 0 again. Okay. That we can see it's not a function. It's definitely something. Because for 2 values of x, we have 2 different y values. Okay. But that's okay. It's a curve. Doesn't have to be a function. X which depends on y. Okay, 3, if I substitute 3, I will have 9 minus 6 and 16 minus 8, I believe, 8. Okay. So these are the points. 8, negative 1, 3, 0, 0, 1, negative 1, 2, 0, 3, 3, 4, 8, 5. Okay, let's try. I don't know. Oh, not straight. This is x, this is y. Okay, 8, negative 1. 8, let's say 8, and this will be negative 1. 3, 0. Oh, wow, okay. I will go 3, 0. It will be here. And then 0, 1, 0, 1, that's the point. And then negative 1, 2, this is the point. Maybe I can make longer y-axis. And then 0 again, 3. Okay, it's a little bit symmetric. And then 3, 4, and 8, 5. Looks like parabola, but... And we can see we have to indicate the direction. That means this was my first dot, which was defined for t negative 2. And then I am going this way. Okay, looks a little bit. I'm just trying to connect these points. That's 3. That's 4. And that's 5. Okay. Just trying to be, but what's important? Important are the directions, and always the arrows indicates that the t value is increasing. This point was for t negative 2. This is for t negative 1. This is for t 0. This is for t 1, 2, 3, and so on. Yeah, we can keep going. That means looks like parabola, and I think it's symmetric. Okay, that means that's our parametric equation. Sometimes, because this looks like quite nice and symmetric curve, what we can try to eliminate the parameter and just get the xy equation. And let's see how we can do it. X is defined like that. 2t minus, t squared minus 2t. Y is defined as a t plus 1. And we have a system of 2 equations. Eliminating the parameter means that I can solve one of the equation for t and substitute to the other one. And looks like the second equation, the y equation, is easy to solve for t. It's y minus 1. And that y minus 1, I will take and substitute instead of t to the first one. And what we getting? We're getting x, t squared will be 1 minus 1 squared, 2 times t, 2 times y minus 1. And I will distribute, I will expand everything. Y minus 1 squared is y squared minus 2y plus 1. I will distribute negative 2y plus 2. And then we have y squared, negative 2y, negative 4y plus 3. Yeah? It looks like the parabola the other way, like x in terms of y instead of y in terms of x. Yeah, that means we get the equation, we get just the Cartesian, like xy equation without the parameter. But of course, I can tell you that's not always the point. The point is to keep the parametric equation. And sometimes it's not even possible to eliminate the parameter. Okay? Sometimes it is, but not always. Especially if the curve is really like fancy, let's say this way. Okay, but we can still, yeah, we should still be able to do it. That means that's the way to eliminate the parameter. Okay, and I have the solution. We can, it's a little bit better, but we can nicely see. And we can also see the distance between the parameter is the same, but because of x and y has totally different like functions, the distance between x and y is not the same. And we can see 8, 3, 0, -1, yeah? But between the parameter, it is the same. And arrows indicates how t was increasing. Okay. Oh, and this is the part that I did eliminate the parameter. Okay. Another thing that we can do, we can have the same, almost the same settings, but we may do some restriction for t. That means, let's say we have identical parametric equations, parametric curve, and we would like to get the graph, but the parameter t, it's only between 0 and 4, right? So we will have something like that. That's the whole, and we remember this was defined for the parameter 0, and this point was defined for the parameter not 1, 4. Okay? And of course, the first point, since we do have a restriction, 0, the parameter, the first value, the smallest value, 0, will give me the initial point, and the parameter t equals to 4, the maximum value, will give me a terminal point. Okay? And we still have the direction. And I think I have this, yeah? Oh, my arrows stays. That's when we can see we have the same parametric equations, but we do have a restriction. And when I substitute A, I have initial point. When I substitute B, it's the last one, terminal point. Okay? Just to know the terminology, if you will have a question, compute the initial point of the parametric curve, or compute the terminal point of the parametric curve. Okay. Now, another example. What curve is represented by the following parametric equations? And this is the equations. X is defined as a cosine of t, y is defined as a sine of t. And we do have a restriction from 0 to 2 pi. Of course, obvious, because otherwise we will repeat probably the same curve. Okay, that means let's try the parameter t. The x value is cosine of t, and y is sine of t. We will have initial point and we will have terminal point. Okay, 0, it's from 0 to 2 pi. Let me put maybe pi over 4, pi over 2, 3 pi over 4, just pi, and then 3 pi over 2. Oh, no, my pen, please cooperate, and 2 pi. Oh, no. Do you remember once? No. Don't do this. 2 pi. I hope it works. Okay. And now you will help me with the unit circle. Cosine values. Can you tell me cosine at 0? And I will try to write cosine at 0 is 1. Cosine at pi over 4? Cosine at 45? Yes, root 2 over 2. Cosine at 90? Good participation. Cosine at 90 is 0. Cosine at 3 pi over 4, which is the same like 45, but is the second quadrant. And cosine in second quadrant is negative, yes? Thank you. Cosine at pi, I think it's again 0, and 3 pi over 2. Oh no, it is 0. Maybe I'm getting crazy. No, cosine, hang on. Cosine, something is wrong. Cosine at pi is, yes, -1, because that's pi, -1. I always draw a function. And then 3 pi over 2 is 0, and 2 pi is again 1. Okay, now sine. Sine at 0 is 0. At 45 is the same. This is 1. This one will be positive. This is 0. This is 1. No, -1. And this is 0. I hope I'm okay. Okay, that means now we can see the point. Let's look at this nice thing. Point 1, 0 is my initial point. And can you see the can you tell me what is the terminal point? The point that I will stop my curve? It's the same. It's like an initial point. That means that I will start and I will finish my curve at the same point. Yeah, it's the same thing. Oh, you probably can guess the shape. I'm worried that my pen is not. Okay, 1, 0. That means this is my initial point. And actually terminal point. And then √2 over √2 is somewhere in the middle. And I will go this way. And then 0, 1. 0, 1. Oh. And then -1, 0. And 0, -1. And back to original point. Okay? I know, looks good, but we, of course, we know the cosine and sine, we know the shape. That means this is simply a circle, right? This is simply a circle with the initial point and terminal point 1, 0, and the trace is counterclockwise direction, correct? Correct, counterclockwise direction. That means this is actually important, yeah, to indicate the initial point and directions. Now, if we would like to, we probably know the equation of the circle, but if we would like to eliminate the parameter, I can simply start with my trigonometric identity. Yeah? Do you remember sine of t, sine square of t plus cosine square of t, it's equal to 1. And sine of t is defined as a y, cosine of t is defined as a x. And I can just switch the order, and this makes sense. X squared plus y squared equals to 1, and that's the equation of the circle with the center 0, 0, and radius 1. Yeah? That means having trigonometric functions is like we always use some identities to eliminate the parameter. Usually, of course, we may have formulas that we can just manipulate the expression. Okay, and this is the solution. Okay, let's keep moving because probably it's that we can see. I really want you to know how to draw a parametric curve and eliminate the parameter. Okay, I have another one. What curve is represented by this parametric equation? X is defined as a sine of 2t, and cosine is defined, y is defined as a cosine of 2t. Again, we have restriction from 0 to 2 pi. Okay, that means now probably the shape will be similar, but something will be different because we switch sine and cosine, and we also have double angle. Let's try parameter t. Now x is sine of 2t and y is cosine function. Okay, 0, and now will be crazy because it's 2 times, let's say pi over 4, then we will have pi over 2, and maybe 3 pi over 4 and pi. Okay, let's do this way first, because we can see if I will repeat, I will multiply everything by 2 anyway. That means sine at 0 is 0. Cosine at 0 is 1. Sine at 2 times pi over 4, it will give me pi over 2. 1, 0. 2 times pi over 2 is pi. This is 0, this is negative 1. 3 pi over 4 times 2 will be 3 pi over 2. Negative 1, 0. And 2 times pi is, of course, 0. And this is the same like 1. That we can see what's happened from starting at 0, 1 and being only halfway with my parameter, I reach my initial point because it's 0, 1. And then if I will repeat everything, let's see what's happened for 2 pi. 2 pi times 2 is 4 pi, but it will be yes, exactly, yes, that's the correct answer. It's the same circle, but we will trace twice. We will trace over again. Let's see. And I believe we have different initial point, because now my initial point, where is my initial point? 0, 1, this is defined for t0. That's the initial point. And which way I'm going? Clockwise or counterclockwise? I think we're going this way, right? Because this is 1, 0, and then, oh, actually I should put my arrows in the middle. 0, negative 1, and then, do I have that point? Negative 1, 0, correct. And then coming back to this one. And this is actually 0, 1. Right? That means this is initial. And what's happened, starting from pi to 2 pi, I will trace the circle again. Yeah? Oh, that's not nice circle. Okay, that's what is, what's the message? The message is that we may have the same curve, because the final output, final picture, it's the same, it's just the circle. And if I will ignore maybe my arrows and initial terminal point, that means we may have the same output, the same curve, but we will have different equation, which of course, having the XY equation, the normal Cartesian equation, we will never have. We have one equation and one unique corresponding curve. For the parametric, it's a little bit different, because we can see the previous example has the same circle, different starting points, different initial point, and different direction, because now actually I am tracing clockwise. The parameter t is increasing clockwise because of the formulas. And I mean, that's one message to take away. And I have the solution. We can nicely see. Of course, we don't have, this is just the blue curve is just showing the tracing. The output is still the pink circle. You know, we don't have like extra, like wider circles. No, it's just showing the tracing. Okay, that means the initial terminal point and the direction. And we trace twice. Okay. Just what I said. We may have the same curve, but different parametric equation. Okay, and let's maybe do one more. Sketch the curve with the parametric equation. X is equal sine of t, and y is sine square of t. And that's interesting. And we have no restriction, but probably we will realize that something is like repeated, because it's still periodic functions. I mean, I will still start from 0, pi over 2 maybe, because now we know what is happening between pi, 3 pi over 2 and 2 pi. And this is just sine of t, and this is sine of t squared. That means 0, 0 squared, 1, 1 squared, 0, 0 squared, negative 1, 1, because we're squaring, and 0, 0. Oh, interesting. What do you think? What is the shape? 0, 0. Actually, I can't really call 0, 0 initial point because we do not have the restriction. T could be any real number. Okay, that means I will, because I pick 0, but we can see we have no restriction. Okay, then I have to go to 1, 1. And I'm going this way. This is point 1, 1. And what is happening from 1, 1? I have to get back to 0, 0. That means actually I'm getting back to 0, 0. And then negative 1, 1. Negative 1, 1. And from negative 1, 1 to 0, 0. That's what do you think? What we will have? We will just go back and forth? Because we will just go, yeah, will be just like the swing, the just, yeah, from 0, 0 to 1, 1, from 1, 1 to 0, 0, and to negative 1, 1, and so on. Do you think we can try to eliminate the parameter and try to look at the equation without t, without that parameter? We have sine of t as a x, and y is defined as a sine of t squared. What I can put instead of sine of t? How sine of t is defined in terms of x or y? Yes, but just instead of sine, what I can put? Sine of t. Oh yeah, we can, Ryan, but you can use the first equation. This is the first, this is the second. It's just x, right? You can see sine of t is just x. Yeah. Actually, what we have? We do have just the parabola x squared. Because sine is defined as a y, I mean y. Y is defined as a x squared. That's nice. But let's actually look a little bit closer because it's just the parabola, but I'm not going like to the infinity. This is actually my limitation. Yeah? And probably you can see why, because x was defined as a sine of t, and sine of t has, I mean the range. It's only between negative 1 and 1. Yeah? Because the sine values for any angle are between negative 1 and 1, then x will be between negative 1 and 1 and makes sense. Now, y is defined as a sine of t squared. That means squared quantity is always positive, and still the maximum value will be less than 1. And makes sense between 0 and 1. That's the reason that we have this limitation, just the parabola between negative 1 and 1. And of course, the directions are important, and we can see it's traced infinitely many times. And we don't really have initial and terminal point because of that. Okay, that means I think you should be good to draw the parametric curve and indicate the initial and terminal points. So now what we will do, the solution. We will skip cycloid. Yes, don't worry, I will not expect like previously, like maybe, I don't know, maybe 10 years ago, I was trying to test the formulas, but this is the nice curve. You probably know the cycloid, yeah, the pink curve. And this one we probably can't really eliminate. I mean, we can eliminate, but it's extremely, eliminate the parameter. But this curve, this kind of like a spring jumping, it's defined like this. X is defined as a r times theta minus sine theta, which of course theta will be, theta is an angle. It's angle, no, it's the circle is making the angle, because we can see when as soon as the circle is like rotating, that angle inside. I don't want to draw it because I don't want to give you the wrong. Okay, no. This point, and let's say this point. That's theta. And then it's like the rotation. The circle is moving, the angle is changing, and the set of dots will create a cycloid. And this is the equation for y. But I can tell you it's not easy to eliminate the parameter and get the xy equation. And we can even see the curve is quite complicated. I mean, it's nice curve. Okay, but don't worry, you don't have to. If I will ask any question about the cycloid, you will have the equation. But no, probably not. Just the simple parabolas. Okay, so now what we will do, since we do have a little bit of time, I will try to add a little bit of calculus to parametric curves. And what I mean by calculus, you have to know how to find a first and second derivative of the curve defined by the parametric equations. Don't worry, we will not really do all of this stuff. Okay? Of course, maybe you can get the tangent line, because if you know the derivative, simply slope of the tangent line is the derivative at the given point, but just the derivative, first and second. No more applications. Okay. So we will apply calculus. And as I said, let's start with the first derivative. Having a parametric equations, f of t and g of t, respectively for x and y. Okay? I will show you a few steps how to get the derivative. Of course, we have to know just the output, the final answer. But let's see how nice it is to see, to have the step-by-step explanation. That means, first of all, what I will do, I will start with the equation, because we remember we may eliminate the parameter in most of the cases. Eliminating the parameter, I will create a new equation, y in terms of x. That means I am pretending that I'm taking this equation, y equals to f of x. But, okay, y is equal to f of x, I still have to remember that y has its own formula, g of t, of course, and x, the inside, the x has its own formula, f of t. My next step is that I did put back. Y is g of t and x is f of t. And I will take this equation, okay, and I will try to differentiate this form, of course, using the chain rule. That means derivative of g of t will be g prime, with respect to t, of course. Derivative of f of t, applying the chain rule, I have derivative of f with respect to the inner function times derivative of the inner function. We remember the chain rule, of course, we do remember. And now I will take this equation and solve for f prime of f of t. Oh, okay, one more step. The f of t, I will rewrite as a x. Right? Everything else, I will keep it. Because actually, since I have this equation, like I did eliminate the parameter, I have just y is equal to f of x. What I'm looking for the derivative, f prime of x. Yeah? That's actually my whole point. That's the reason that I rewrite f of t as a x, and now I can take this line and solve for f of x, f prime of x. F prime of x is just g prime over f prime with respect to t. Right? I mean, it's a little bit weird at the moment, but that's how we can think. We can always look at the parametric curve and we can think that, oh, probably I can eliminate the parameter and I will have my equation in terms of x. In order to get the derivative of this, I have to just differentiate g, which is x, not x. It's y, derivative of y, over derivative of x. And probably reminds you something, dy dx, right? Derivative of the function y with respect to x. That means it is simply like that. I will just make the summary. Having x formula and y formula, in order to get the derivative, f prime, I will differentiate y and divide by derivative of x. That's it. That's the first derivative. Okay, that means this is simply the derivative of the, and we don't even have to eliminate the parameter because we still need the formulas. In order to get the derivative, we will differentiate y over derivative of x. They both are in terms of t, but that's how it works. And then we can, of course, we can find some tangent lines to the parametric curves, but we will do this. Do I have the notes? No, I don't have the notes now because I have later. In order to find the tangent line, let's say horizontal tangent. Okay? Horizontal tangent means that the derivative is 0. Okay? That means for the horizontal tangent, I have to say, because this is my derivative, right? Derivative is a fraction. Fraction is 0 if the top is 0. That means in order to find the horizontal tangent, I will just solve this equation. Horizontal tangent, because we like this. Now, if I will say, what condition, maybe I can ask you, what condition I have to set up for the vertical tangent? Vertical tangent. What is the slope of the vertical lines? Oh, no, the slope of the horizontal lines are 0. What about the vertical lines? It's like infinity, or we can say undefined. Yes, Jove, yeah, that's good. Yeah, Ryan, you probably said for the horizontal. That means for the vertical, we have undefined slope. Now, algebraically, if you're looking at the fraction, when the fraction is undefined, what must happen if the denominator is 0? Right? That means this is, because it's interesting, because we do have like a formula for x and for y. That means if x prime is 0, then we will have vertical tangents at this point. If y prime is 0, we will have horizontal tangent. Yeah, just a little bit of application. But first of all, let's practice derivative. Okay, I have 3 functions, and let's see. Find the derivative of the following parametric curves. The first one is defined as x is 6 sine of t, and y is t squared plus t. Okay? Probably crazy curve, I don't even know, because it's trigonometric and the quadratic, but we don't have to draw it, we have to just find the derivative. Derivative of y over derivative of x. Derivative of y is 2t plus 1 and 6, oh no, my pen, 6 cosine of t. Done. Yeah, you can see just like that. So nice and easy. Now, derivative of y over derivative of x. Y prime, x prime. What is y prime? It's actually the same, 2t plus 1 over 2t. Maybe this one I can simplify. I can divide 2t over 2t, and I can divide 1 over 2t. Just, I don't know. Maybe it's easier this way. Okay, and then the last one, y prime, x prime. Y prime is negative 3 sine of t, and x prime is 2 cosine of t. I can rewrite. Can you tell me a function sine of t over cosine of t? Yes, done. Thank you, Ryan. Tangent of t, yeah, just in case. And I can box the final answers. But we can see it's not bad. Of course, maybe it's not helpful to simplify when we're looking for the horizontal or vertical tangent, yeah, because we really need the denominator and numerator to focus on. But for the final answer, it's always nice to simplify. Okay, that means I think you should be okay, more than okay with the first derivative. Okay, that means this is the notes that I was trying to explain. For the horizontal, just derivative of y is 0. For the vertical tangent, derivative of x is 0. Yeah. And I think I have a question for this. But okay, before the horizontal and vertical, let's try to answer just the question which is related to tangent line, but I don't know if it's vertical or horizontal. That means typical question, okay, asking for the derivative, but through the tangent line. Find the slope of the tangent line for the following parametric curve, and we recognize x is 6 sine t, y is t squared plus t at the point 0, 0. Right? Because you probably notice we do have one extra thing to do. 1, 6. Okay, let's try. Slope of the tangent. Of course, slope of the tangent, it will be the derivative. Derivative is y prime, x prime. 2t plus 1 over 6 cosine of t. Okay, but now my derivative is in terms of t. That means what value of t I have to substitute, and I only know x and y. Okay, that means this is one extra step, yeah? One extra step that for the value, 0 for x, 0 for y, what is the corresponding parameter? Okay, what we have to do, we simply have to substitute. X is defined as a 6 sine of t. No. Let's do this way. X is defined as a 6 sine of t. Okay, I can put this. And t squared plus t is y. 6 sine of t, and I want x to be, that means that's the extra thing. I want x to be 0, and the same t squared plus t, y, I want to be 0. And I can solve this equation for t. I can divide by 6, and sine for what angle is 0? For 0, pi, 2 pi, and so on. But let me stop here. That means now because what we have to do, we may have lots of values of the parameter t that will give me x0, but I have to match. That means let's solve the other equation and let's pick the common answer, because not only x must be 0, also at the same time y must be 0, and the parameter t must be the same for both of them. Okay, for this one I have quadratic equation. I can factor out t, and we can see t is 0 or t is negative 1. Right? Because from this one is negative 1. That means what is the answer? That the same value. We have to pick the same value of the parameter t. If t is 0, and actually, right, it's also, that means we get lucky just in this case. That means if the parameter t is 0, then x and y is also 0. Right? But not always. This is just really coincident that 0 is matching to that value. Okay? That means actually, I think, Ryan, you might be correct, because 2 times 0 plus 1 over 6 times cosine of 0, I can write here, it is 1 over 6. because this will be 0, 1, cosine at 0 is 1. That means you, yes, you actually lucky, yes. Yeah, but please remember, we have to figure out the parameter t. Let's try another one. Hopefully will be different. Okay, let's try this one. Because now the x and y value is 2, 2. I'm really hoping the parameter t is different. Okay, the same thing. Find the slope of the tangent line. Slope is just the derivative, y prime, x prime. Y prime is 2t plus 1, and x prime is 2t. Oh, okay. But now I need the same thing. Let's maybe do this one. T squared plus 1, that's x, and this must be 2, because x is 2. Let's try to solve it. And y, it's also 2. T squared plus t is 2. This one will be just 1. That means I have 1 or negative 1. Okay? This one is t squared plus t minus 2, quadratic equation. I can factor out. Yeah, I think it's 1. We have 2 and 1, plus and minus. Okay, that means t is 1 or t is negative 2. Okay, that means t is definitely, because we can see negative 1 will give me x2, but t negative 1 will not give me y2. I have to have the same parameter, because parameter t equals to 1 will give me my corresponding point 2, 2. Okay, that means t is 1. And what is the slope? 2 times 1 plus 1, 2 times 1. 3 halves, thank you for computing with me. Okay, as we can see, that's the typical way to check the derivative, finding the slope of the tangent line. Okay. We will skip this one maybe, because I still want to show you the second derivative. You can try this one, it's just the same way that I did. Okay, second derivative. Yes, because I still want to show you the second derivative. Yes, second derivative will be probably, of course, the derivative of the first derivative. Yeah, that's the second derivative. But we will have one extra thing that sometimes we think it's maybe like strange because of this extra parameter. But yeah, let's see. Second derivative, it's like, that's the notation, like d squared y dx squared, but it's simply, yeah, it's simply the derivative of the first derivative. Ryan is saying that no, I don't think we will use the quotient rule, but I like the second half of your comment, divided by x prime. Okay, that's what I was kind of referring, that it's maybe strange. But let's see. This is the notation, which means actually this, derivative with respect to x of the first derivative, because this is just the first derivative, okay, and this is just derivative. But you notice my notation is with respect x and y. We still have to think about the parameter. That's how we can read this. Derivative with respect to x of the first derivative. That's of course the second derivative. Second derivative. Yeah, we know second means the second derivative. First means the first derivative. That means second derivative, that's the notation. It's the derivative of the first derivative. But let's see, because we do have to put t. I can show you this. That's what we will do. We will differentiate with respect to t, the first derivative, and everything with respect to x, of course. That means derivative with respect to t of the first derivative, and still with respect to x. Which means the denominator will be the same like for the first derivative. Okay, I can maybe write this. That means this will be you will just take the first derivative with respect to t and differentiate. But please remember, we have to divide by derivative of x. That means this is kind of like the weird thing. Maybe it's not weird, but that's how it is. In order to take the second derivative, again, we will differentiate the first one, of course, but remember, divide by still by derivative of the x with respect to t, of course. And I kind of, yeah, that's the same thing. All right, that's, please remember, normally we will differentiate the first over derivative of x. And this is just the first derivative. Okay? Which means denominator of the first and the second derivative is identical because everything is with respect to x. And x has its own formula. That's the reason. Okay? And we can try. Even this one. We remember the first derivative, I can put with respect to t. Y prime, x prime, 2t plus 1, 6 cosine of t. Okay. And now the second derivative, it will be, how can I write? Derivative with respect to t of the first one. No, I don't like, let's say this, but still derivative of x, because everything is with respect to x. And this means that I have to take this derivative and differentiate derivative of the first derivative. And can you tell me what I have to put in the denominator? Can somebody, it's still the same, it's still the, no, just 6 cosine of t. Oh, no, we do not differentiate, we just differentiate x. Yeah, just the same thing. That's what I was saying. Denominator of the first derivative is the same like denominator of the second derivative. Or I can even indicate with different color. X prime and x prime. That's the thing. And actually, I must come back to your comment, Ryan. You're right, we will use the quotient rule. Okay? But what I was saying, I mean, not always the first derivative will be the quotient. If the first derivative is simple, we will not really use the quotient rule. Because actually your description fits perfectly to this example. Quotient of the first derivative and then dividing by x prime. But not always, right? Not always f prime will be the quotient. That's when we can't really make the general statement. Okay, and let's try. Looks complicated, but hopefully I can do it. The quotient rule. 2t plus 1 is derivative is 2 times denominator minus 2t plus 1, and derivative of 6 cosine of t is 6 sine of t, negative. I will change for the positive. And all over denominator squared, 36 cosine square of t, and still 6 cosine of t. Okay, I can probably just rewrite as a one fraction, 36 times 6, or I can write 6 cube cosine cube, and this will be 12 cosine of t plus 12t sine of t, I'm just distributing, and 6 sine of t. Oh, we do have to, no, the common factors too, but okay, we can just leave it. But we can see that's my point, yeah, to keep this, differentiate the first derivative, dividing by the x prime. And let's, maybe we can do this one. First derivative, easy. Y prime, x prime. That's x prime. Y prime is 2t plus 1, and this is just 2t. And we can simplify. All right, that means this is my first derivative. Now, I can maybe write this notation. Second derivative will be derivative with respect to t of the first derivative all over x prime. Right? That means I will differentiate with respect to t my first derivative and still divide by 2t. Okay? Please remember about this. Okay, and now we can see we don't even have to use the quotient rule. That's just my point. Yeah, but overall, usually it is quotient, right? Okay, what's the derivative? I can copy half. 1 over t is negative 1 over t squared over 2t. Negative 4t cubed. I believe I make derivative of 1 over t is negative 1 over t squared. And then I copy 1/2. Okay, you can correct my calculations, but I think it's good. Okay, well, that means please remember about this denominator because that's the only thing that we forgot sometimes. Okay, and I have, do we have time? No, we will skip this one. We will skip this one. Let's just, because I don't know if we have enough time, but let's just set up a few things for this question, okay? I know I will keep you maybe like 5 more minutes. Because this one is just the horizontal and vertical. That's what I wanted to. I started and I would like to finish with this. Okay, that's we have parametric equation. T squared for x, t cubed minus 3t for y. And we have a few parts. The first one is telling me that I have to show that this curve has 2 tangents at the point 3, 0. 2 tangents. I mean, I can probably guess that that curve is like intersecting, right? And I know that it's intersecting. Do I have the curve? Because because how it is possible that we have 2 tangents? If we will have like, let's say like a loop, at one point I can have 1 tangent and I can have another one, okay? And that's actually, the curve looks like a loop. I can show you the curve. When you see the blue curve, and at point 3, 0, we will have 1 tangent and another one because it's intersecting, okay? But how we can do this, we can simply treat this part A as a question like find a tangent line, maybe, at the point 3, 0. And we know how to do this because we can try to find the derivative first. Yes, slope of the tangent is the derivative y prime x prime. And y prime is 3t squared minus 3, and x prime is just 2t. But I need the t value. X is 3, y is 0. X is t squared must be 3, then t is plus or minus square root of 3. Y is t cubed minus 3t is 0. I can factor out t, and we can see I have 0, that's actually 3, or positive and negative square root of 3. Okay, and now what's happened? Which values of t are the same? The square root of 3 and negative square root of 3. That's the reason that we will have 2 tangents. And we can compute possibly the slope. If you substitute positive root 3, 3 times 3, 9, this will be 6 to square root of 3. And if I substitute negative square root of 3, also 6, but negative square root of 3. I can definitely simplify, divide by 3, and rationalize. I think it's just this. If you rationalize denominator, and of course divide 6 by 2. Square root of 3 times square root of 3, and this will be gone. Okay, that means actually the same thing. That's weird. Parameter is the same like a slope. Of course, coincident. Okay, even, okay, no, we can keep it. I don't want to confuse you, but you know where that value comes from. Okay, but we can see two values of t match. That's the reason that we have two tangents. Okay, now who can tell me the condition for the horizontal tangent? What equation I have to solve for horizontal? Horizontal. For horizontal, y prime must be 0. And y prime is simply 3t squared minus 3. I can factor out 3, and I have the parameter 1 and negative 1. At 1, at negative 1, if parameter t is 1, then it's horizontal tangent. Horizontal tangent. Can you tell me what's the value for x and y if the parameter t is 1? Who can tell me what will be the corresponding point if the parameter t is 1? Well, you can just substitute here. X will be 1 and y will be negative 2. Okay? I'm just substituting here. And now you can give me this answer. What is the value of x and y if t, the parameter t, is negative 1? It is 1 and positive 2. Yes, I think it's positive 2. Yes, thank you. I was trying to compute. As we can see, at the point 1, negative 2 and 1, positive 2, horizontal tangent. Shall we check? Yes, 1, 2 and 1, negative 2. Horizontal tangent. Let's check the vertical tangent. Who can tell me for the what's the condition for the vertical tangent? Vertical tangent. For the vertical tangent, x prime is 0, and x prime was just 2t. T is 0. If t is 0, who can tell me x and y values? Just to have the big picture, 0, 0, of course, because it's 0, 0. And I think, I didn't want to mention before, but you can see that's the vertical, 0, 0, vertical tangent. Great. That means you definitely know. And do we have the first derivative? That's the first derivative, because I just want to check that you will get the second derivative. And yeah, that you can see, that's the second derivative. Oh, I did simplify. Okay, shall we do it again? Because I don't. Okay, what was the first derivative? Shall I copy 3t squared minus 3 over 2t? Okay, that you can see I did simplify a little bit just to avoid the quotient rule. I mean, I can possibly I can divide. That means we will have 3/2 t minus 3 over 2t. I just divide like that. It's still okay. Am I right? Why I have addition here? Is this correct? Yeah, I think. No, hang on. What is the first? 3t squared minus 3 over 2t. That's my first derivative. 3t squared. Oh. No, but the derivative, it's 3. Right? I'm just trying to, I don't think this is my good derivative. Okay, that's definitely the first derivative. Let's check. 3t squared minus 3 over 2t. Okay. And I just divide like that. 3t squared over 2t will be 3/2 t, and this will be negative 3 over 2t. Let's differentiate again. Right? That means I will differentiate with respect to t this, and you will help me. Oh, that's the derivative. I think this is correct. Now I'm seeing this. And let's divide by derivative of x. Remember that. I know that I'm stressing out this. Okay, derivative of 3 over 2t is just 3 over 2. And derivative of 3, this is constant. But 1 over t is negative 1 over t squared. Then I can change this for positive, because negative and negative will give me positive. And derivative of x, it's still 2t. Okay, we do have 3 halves, 1 plus this. And I can drop 2. And I can also get a common denominator, t squared plus 1 over t squared and t. And I can drop that t squared down. So I believe I have correct derivative on the top. Dropping this down, we have cube. Okay. Of course, it's the way to simplify. For me, the important part is this one. Okay, or maybe this too, because then you're differentiating. Remember about the x prime. Okay, let me switch off the camera. Okay, I'm here. That's pretty much everything. Okay, that means tomorrow I will probably not run like a live session. I will be still in the classroom. Okay? If you have some questions, please visit me. And please ask, and I can share the white screen, I can solve some problems. If not, you can just post the question on the discussion board, or you can email me, okay? That means tomorrow will be not like a live lecture, because I did cover everything for this week in this, today, okay? That means parametric curves, first derivative, and the second derivative, and horizontal and vertical tangents, okay? Okay, thank you very much for today. Thank you for your participation.